everybody, Mr. Covey here, and this is going to be a quick video, don't worry. And it is on polynomial regressions on your calculator, okay? Oops, sorry. I know that sounds kind of fancy, but we've already done this 2 times, actually. We're just kind of extending it a little bit. So when I say polynomial regressions, we've actually already done 2 of those. We've done linear regressions. Again, if that vocab word isn't like coming out in your head, or you're connecting with something in your head, lines of best fit. Remember when we did lines of best fit? Those were linear regressions, finding a line that fits data. Okay, so this is real world data and trying to find a line that fits it best. And we did that at the beginning of the year. We also did the same exact thing when we studied parabolas. We called that quadratic regressions. Okay, we looked at some data from real world and we found the parabola that fit that data. Both of these were on your final. You guys did a good job on those. Remember that these were basically the exact same process, only you chose to try and find a parabola that fit the data instead of trying to find a line that fit the data. Okay. And all we're doing now is we're extending this and saying, hey, if you can find the line of best fit or a parabola of best fit, I bet you can find a cubic of best fit or a quartic of best fit. You can find not only a 1st degree polynomial or a 2nd degree polynomial, you can find a 3rd degree polynomial or a 4th degree polynomial that fits the data, okay? And why would you want to do this? Well, it just depends on how complicated your data is. Sometimes a linear regression is going to fit it well. Sometimes you're going to need a parabola to fit it. Sometimes you're going to need a 3rd degree. Sometimes you're going to need a 4th degree. You kind of have to keep going until you find one that fits well enough is really the idea here. I really have very little new things to tell you about this because it works exactly like how we did linear regressions and quadratic regressions. Okay, so I'm just going to go through a couple examples with you, and then I'll let you guys do the bottom 2. Okay, so this first one says the table shows a person's billable hourly fee, Y, in dollars, in the year T, when T equals 1 corresponds to 2005. Find the polynomial model for the data and use the model to estimate the fee in 2012. Okay, so we have this table here with X's and Y's. They don't use X, they use T, but same thing. And I want to find out what type of polynomial will fit it best. Okay, the first thing we got to do is put it in our calculator. Okay, so go ahead and pause and do that. Okay, I hope you remember that. We've done that in a few different chapters. So you hit stat, enter, you enter your data. Okay, once you got your data in there, we're going to do the same thing we've been doing, which is you want to find something that fits the data, you hit stat, you go over to calculate. We've done a lot with 4 and 5, finding a line of best fit and a quadratic of best fit. But if you see right below, those 6 and 7 are a cubic and a quartic, 3rd degree and 4th degree. Now, the kind of tricky part is to tell which one of these is going to fit this data. There's a few ways to do that, but the easiest way is just to try out the different ones. So I'm going to say, hey, maybe this just has a line of best fit. I'm going to hit enter. I'm going to hit enter. It's going to pop up my line of best fit. I want to look at the R squared now. So let's look at the R squared, and it's 0.38. Not good. Remember, I want my R squared to be really close to 1. Okay, so that's kind of the important thing to jot down here. You want R squared close to 1. And if you got your R squared close to 1, then that model is going to be good enough. Okay, but here, we're not close to 1 at all. And by close to 1, I mean like 0.9 something. So I'm going to go back to stat. I'm going to go back to calculate. I'm going to say, hey, a line didn't fit it. Maybe a parabola will. Maybe a 2nd degree polynomial will. Do a quadratic regression. The R squared is 0.86. It's okay. I feel like I can do a little bit better. I really want to be at least at 0.9. So I'm going to go back to stat. I'm going to go back to calculate. I'm going to say, hey, maybe I need a 3rd degree to fit this data. Okay. I'm going to do my cubic regression. There we go. I got R squared is 0.99966. Okay. This is a really close to 1, meaning a cubic function is going to fit this data super, super closely. Okay, so if you remember visually, this cubic that they're describing here is almost going to go perfectly through all of these points. Okay, how do we get that cubic? Well, look, it gave it to us in standard form. So y equals something x cubed plus something x squared plus something x plus a number. They tell us all of the coefficients. So 1.47x cubed plus, so it's actually minus here, minus 11.73x squared plus 25.37x plus 5. Okay. And this equation here is a cubic equation, third degree, that fits this data really well. That's it. Now I can use this to answer whatever question they're asking me. They're saying, hey, use the model to estimate the fee in 2012. Okay, well, if t equals 1 is 2005, 2012 is going to be 7 or 8. Let's be careful here. So 2005, 2006, 2007, 2008, 2009, 2010, 11, 12. It's going to be 8. Be careful with the counting there. I almost messed that up. So I'm going to want to use a t value of 8, and I want to figure out the y when t or x equals 8. Just going to plug in 8 for all the x's. See what I get out. Let's do that real quick. 1 point. Oops. Let's clear all this out. 1.47 times 8 cubed. That's 11.73. Oops, sorry. X squared. That's 25. Oops, I don't want an X, I want an 8. My bad. Oops, and up here I forgot to put a times sign. My math game's all off here. 7.73 times 8 squared. Okay, and then times 8 plus 5. All right, so now that we got that all typed in, we're going to hit enter. And we get our prediction out. Okay, $209.88. Okay. Cool. Why don't you go ahead and try and do the second one, and then pause the video, do that, and unpause, and we'll check. Okay. So for this one here, put your data in the calculator. I did a linear regression, and I got, if you look over on my calculator here, I got r squared is 0.98. That was good enough. As long as I have 0.9 or better, I'm going with it. Okay, so I said, hey, I'm just going to use a line of best fit. Here was the y equals mx plus b that they spit out, that y equals ax plus b. Use it to calculate the age in human years if the cat age was 3, or the cat years if the human age was 3. And I got out 26.37 years. Okay. All right. Why don't you go ahead and do one more of these, and then we can save the last one. Okay, so go ahead and try and do this one. Pause the video, go through it, unpause, and we'll chat. Okay, so a little geometry connection here. You guys will talk about stuff like this a lot next year, or actually only a few months from now. And I went through, and a line of best fit didn't work well. And so I did a quadratic regression, and look what happened. My r squared here was exactly 1. So if you remember when your r squared, or your r is exactly 1, that means it's not even approximating the data like pretty good. It's approximating it perfectly well. Okay, so it's like the perfect model to use. So I didn't look at a cubic or a quartic. I stopped right there. I said, I'm going to use this parabola. Here's the equation the calculator gave me. It said, determine the number of diagonals in a decagon. If you didn't know that vocab word, that's okay. But you might be able to figure out that a decagon is a 10-sided shape. So I plugged in 10 for the number of sides. and I got out that there'd be 35 diagonals. If you didn't know that word, don't worry about that. Cool. All right, and we can leave this last one to practice with in class, and that concludes this video.